Hello, my name is John Davis. I'm an undergraduate researcher in the IDEA Lab at Oregon State University. Today, I will be presenting learning over dirty data without cleaning. Data cleaning is a major obstacle in machine learning. About 60% of a data scientist's time is spent cleaning and organizing data. This is because real-world data sets are dirty. They contain duplicates and other inconsistencies. Dirty data significantly reduces the accuracy of learning. We look at IMDb, a movie database that contains movie-relevant information such as year of creation, director, and genre. We couple this information with positive and negative examples of movies that did well at the box office and poorly at the box office. We want to use this information to predict whether a movie will be high grossing or not. The key limitation of the IMDb movie database is that it does not contain financial information about a movie. However, the OMDB database does. It contains information such as distributor and budget. However, there's a key problem in the fact that titles in OMDB and IMDb are in different formats in both datasets. That means the same movie might be referred to by a different title in both datasets. This prohibits us from learning. Current approaches to data cleaning are difficult and time-consuming. Pre-processing is a necessary step in order to clean the data before it can be ingested into a machine learning algorithm. This step requires significant manual effort and a ton of computational and financial resources. Our question is, can we eliminate the data cleaning step altogether? And our goal is to learn accurate models directly over the dirty data. Our approach is to guide the learning algorithm to deal with the dirty data using high-level guidance on data cleaning. The advantage to this approach is that the algorithm considers and cleans only a subset of data relevant to the model. The challenges of this high-level guidance is that it must be easy to provide, and the integration into the learning algorithm must be easy. Luckily, we have data constraints, which describe the properties of clean data. They're declarative so that they are easy to write, and they are also found in databases, for example, functional dependencies. We focus on two representative types of constraints, conditional functional dependencies and matching dependencies. Conditional functional dependencies generalize traditional functional dependencies. A plain text example of this is movies with the same title must be made in the same year if they are made in the same country. However, as we can see, IMDb has violations of this CFD. In the first two tuples, the titles and the countries are the same, however, the years are not. The challenge here is that it's hard to pinpoint the clean version of the data. There are several different possible repairs to resolve the violation of the CFD. However, it is unclear which repair is accurate. You can change the title or the year. This leads us to have numerous possible repair databases for a single large dirty database. The next constraint we look at is the matching dependency, which resolves duplicates and connects entities. A plain text example of this constraint is if movies across two tables have a sufficiently similar title, then they have the same title. An example of this is Hunger Games, the in IMDb is sufficiently similar to the Hunger Games in OMDB. However, looking closely, there are several different sufficiently similar titles in OMDB, which signify the different repairs that can be made. However, it is unclear which repair is correct. Current cleaning systems materialize repair databases for learning. The first challenge here is managing many repair databases. There are a couple different ways to do this. The first is to generate one or a minimally repaired database, which is shown to be inaccurate. The second is to allow for violations of constraints. However, this also leads to inaccurate learning because the data is dirty. Finally, you can support only attributes with finite domains. However, this does not cover most real-world data because attributes are often infinite. The second challenge is to produce another manually cleaned database. However, if the underlying data changes, you have to recreate the lengthy process to get another manually created repair database. Our solution is to produce and generalize repairs while learning. This addresses the problem of having too many repair databases because it encodes the repairs in the hypothesis language of the learner instead of actually producing the repair databases. It also only produces repairs relevant to the model. Finally, in the generalization step in the learning, it reduces the variation in the model, which will also reduce the number of repairs. For the purpose of this paper, we focus on relational machine learning. Non-relational machine learning, for example, linear regression and neural nets, assumes that data is IID, or that there is no dependency in the data. However, this assumption is not true in relational data. This is why we must use relational machine learning to learn over non-IID data. An example of relational learning is shown below. There are 3 tables and positive and negative examples which are fed into the relational learning algorithm. The output is a weighted data log definition with one or many clauses. Each clause has a head literal, or the target definition, and body literals, which make up attributes that are relevant to the target definition. The first clause in this example data log definition says that a high-grossing movie is one made in the United States and of the action genre. In order to predict a new example, we check to see if the learned definition covers the example. We do this by feeding the data log definition a new example and classifying it as positive or negative. Our learning algorithm, DirtyLearn or DLearn, extends current relational learning algorithms. It uses a bottom-up approach, which starts by using a positive example to create the most specific definition. It then uses other new examples to generalize and improve the model until it covers the most positive examples and the least negative examples. The first step is to create the most specific definition for an example. We give DLearn a positive example, in this case the Hunger Games, as well as a data constraint. In this case, it's a matching dependency. That means that similarity between titles equals equality. We first gather the relevant information from the IMDb database and add it to the data log definition. We then notice that in order to get OMDB attributes, we have to exercise this matching dependency. Here we introduce a repair literal that signifies the 2 different repairs that can be made to link the IMDb movie with the OMDB database. The DLearn learn definition here actually compactly represents 2 different repair definitions. The repair definitions are valid over a distinct repair database. The second step is to generalize the definition to cover other examples. One method of generalization is to drop literals in order to change the definition. This covers more positive examples. In this instance, we add John Wick as another example. How do we define coverage for definitions with repair literals? Does our data log definition cover an example is the question we ask. Since our definition has multiple repair definitions, we want to decide whether to use all or some of the repair definitions and see if they cover the example in all or some of the repair databases. To make this decision, we use a semantic that is not too restrictive and not too loose. DLearn hits a middle ground. Does our definition cover a positive example? The definition is said to cover a positive example if each repair definition covers the example in some repair database. Similarly, we ask, does our definition cover a negative example? Our definition covers a negative example if at least one of its repair definitions covers the example in some repair database. Here we show the generalization step. We extend current generalization methods, for example, dropping literals, to satisfy our semantic. The generalization also drops repair literals to reduce the number of possible repairs. In this example, we introduce John Wick, which has the distributor Lionsgate. In order to cover this example, we have to drop the body literal that says the distributor is Sony, and we also drop the related matching literal, or the repair literal. This allows us to create a smaller and more generalized data log definition which covers more positive examples. When do we stop generalizing? We compute a score to ensure a definition covers enough positives and not too many negatives. For example, the number of covered positives minus the number of negatives. It is challenging to compute the coverage score of a definition over many examples. The question is, how many examples does our definition cover? The naive approach to solve this problem would be to produce all of its repaired definitions and compute the coverage over all the repaired databases. However, this is very time consuming because there are too many repaired definitions and we have to produce many repaired databases. We extend and use subsumption checking between data log definitions. We do this by creating the most specific definition for every example called the ground definition, which is done once per example. We then check if the definition subsumes the ground definition for each example, and if the data log definition covers the example only if the definition subsumes the ground definition. This does not generate the repaired definitions or the repaired databases, so it computes the scores efficiently. The proof for this and other interesting results can be found in the paper. Our empirical study implements DLearn on top of an in-memory relational database, VoltDB. We use 3 different sets of 2 data sets with varying levels of matching dependencies and conditional functional dependencies. We compare our system, dlearn, to 2 baselines, the first being a relational learner directly over the dirty database. The second is a manual cleaning effort to create a single repair database, which is then fed into the relational learning model. The third is our system. The first experiment we run only considers matching dependencies. We find here that dlearn is more effective than other baseline solutions. Dlearn is also reasonably efficient because it does not need the manual cleaning, which the repair database does. The second experiment considers both matching dependencies and conditional functional dependencies. Here we test varying levels of randomly injected CFD violations into the datasets. We see that dlearn is significantly more effective at learning an accurate model than the other baseline. We conclude that you can use constraints in learning to eliminate cleaning and to learn effective models efficiently. Using data constraints and dirty data, we can use a learning algorithm directly over the dirty data to create an accurate model. Removing the cleaning step from the data analytics workflow creates a happy data scientist. The next step is to extend this into other learning models and other types of errors. Thank you.